We call it the universe's graveyard, a place where light itself surrenders, where matter is erased without a trace, where everything that ever falls in is gone forever. The black hole, the ultimate destroyer. But what if everything we think we know about these cosmic monsters is pointing us toward a conclusion that is completely wrong? What if the end is not an end at all? A small group of physicists now believes the black hole is not a tomb, but a womb. So why are they so convinced that the grave is actually the birthplace of new universes? Black holes have this reputation as cosmic vacuum cleaners, roaming monsters that drift through the galaxy, tearing everything apart. You see them in movies as these terrifying, unstoppable forces that swallow entire planets whole. It's a great story, but it's not the reality. According to NASA's findings in 2022, the common belief that black holes are wandering predators is simply wrong. The truth is that black holes are actually anchored at the centers of galaxies, holding entire solar systems in orbit around them like a gravitational keystone. The idea that a black hole sucks everything in like a giant vacuum cleaner is another misconception that NASA has directly addressed since 2021. Black hole only pulls in matter that crosses its event horizon, the true point of no return. Anything that stays a safe distance away orbits it exactly like planets orbit a star, completely undisturbed. If our sun were suddenly replaced by a black hole of the same mass, Earth would continue its orbit without missing a beat. The gravity we feel would be identical, just with a lot less sunlight. In fact, you are living in the orbit of a supermassive black hole right now. Our galaxy, the Milky Way, has one at its very core called Sagittarius A, and our entire solar system takes about 230 million years to complete a single lap around it. That means the last time we finished one full orbit, dinosaurs had only just begun their reign on Earth. So when you look up at the night sky, you are not looking at a chaotic void. You are looking at the gravitational heart of our galactic home. So if these objects are not chaotic destroyers, if they are stable and predictable enough to anchor whole galaxies, then what exactly happens to matter when it gets pulled in? Because something is clearly going on at that event horizon, and the answer to that question will completely shatter everything you thought you knew about what a black hole really is. That last thought lingers in your mind as you realize the implications. For decades, films and sensational headlines have painted black holes as cosmic vampires, drifting through space and randomly swallowing anything unlucky enough to cross their path. But the reality, as you now see, is almost the opposite. These objects are not vagabonds at all. They are the silent, steady anchors around which entire galaxies spin. The misconception likely stems from a simple confusion between the concept of gravity and the idea of a vacuum cleaner. A black hole does not suck in the same way a blender does. It only influences things that wander too close to its gravitational well. Most matter in a galaxy, including our own sun and every planet in our solar system, orbits safely at a distance that keeps us from being pulled in. The gravitational pull of Sagittarius A is strong, yes, but it is not all-consuming. Scientists at NASA have been working to correct this image for years. They point out that matter swirling close to the event horizon acts like water circling a drain, but that metaphor fails to convey just how stable and ordered that motion actually is. The material in the accretion disk moves at incredible speeds, but it does not spiral inward randomly. It maintains a delicate balance between centrifugal force and gravitational pull. Only when matter loses angular momentum, perhaps through collisions or magnetic interactions, does it slowly drift toward the point of no return. And even then, that process takes thousands of years for a single particle. The idea of a black hole suddenly appearing behind a star and swallowing it whole, that is pure fiction reserved for B-movies. In truth, our galaxy has orbited Sagittarius A for over 13 billion years, and it has not devoured a single star in that time. You might wonder if this means black holes are passive and boring. Far from it. They are the engines of cosmic evolution. The material that does eventually cross the event horizon contributes to the black hole's mass, which in turn strengthens its gravitational influence on the entire galaxy. It is a symbiotic relationship, not a predatory one. As you sit there absorbing this information, you experience a subtle shift in perspective. The night sky feels less like a minefield and more like a quiet, orderly dance. The question that now burns on your tongue is this: if the event horizon is not a violent shredder, then what does it actually feel like to approach it? What truly happens on the other side of that boundary? Every physicist who has ever pondered this has hinted at something deeply counterintuitive, something that defies our earthly understanding of time and space. The answer, as you are about to discover, lies not in destruction but in a total transformation of reality itself. In 1974, a 44-year-old physicist named Stephen Hawking stood before a gathering at a conference on gravity in Oxford, ready to present an idea so strange it would unsettle the foundations of astrophysics. He had been working through the mathematics of black holes, Those objects long considered the universe's ultimate dead ends, and he believed he had found something no one else had seen. In his notes was a claim that black holes, the great cosmic eaters, could actually emit radiation. As he finished laying out his argument, a young colleague leaned over and asked him a question that would become a haunting echo for decades. If a black hole gives off radiation and eventually fades away, what happens to all the information that fell into it? Hawking paused. That single question, posed in a quiet room in Oxford, would consume the next 40 years of his life and send theoretical physics chasing after an answer that still has not fully arrived. His original revelation, published that same year in Nature, was that black holes are not completely black. They glow faintly because of quantum effects occurring near the boundary where light itself becomes trapped. This boundary, the event horizon, is not a hard wall but a region where the rules of quantum mechanics and gravity collide. Hawking showed that pairs of particles are constantly being created at this edge, and sometimes one of them escapes while its partner is pulled in. That escaping particle carries away a tiny piece of the black hole's energy, which means the black hole slowly loses mass over time. It is a process that would sound almost poetic if it were not so devastating to older theories. The universe's most destructive objects are literally evaporating, particle by particle, into nothing. The mechanism scales in a strange way, because the smaller the black hole becomes, the hotter it burns and the faster it disappears, which makes the final moments of its life a rapid, blazing finale rather than a slow fade. A single black hole with the mass of our Sun would need 10 to the 67th years to vanish completely, a span so vast that it dwarfs the age of the universe, which stands at just 1.38 times 10 to the 10th years. To write that number out would be to count more zeros than there are grains of sand on every beach on Earth. And yet even that unimaginable duration is finite. The black hole will not be there forever. The realization that these objects have a life cycle changes everything about how we must think about them, because it destroys the comfortable image of a permanent cosmic graveyard. If Hawking was right, and the physics community has largely accepted that he was, then black holes are not static monuments to destruction. They are dynamic, temporary, and ultimately mortal. The matter that gets consumed inside them does not simply vanish into an eternal vault. It gets processed, transformed, and slowly released back into the universe in a different form. When you turn that idea over in your mind, when you really sit with it, you understand that the old story of the black hole as a one-way ticket to oblivion was always incomplete. The question that remains, the one that Hawking could not shake, is what is happening at the very center of these objects while they live. If the radiation at the edge is real, if the black hole will eventually dissolve into nothing, then what about the singularity at its heart, the point where the laws of physics as we understand them collapse into infinity? You can read the original paper in Nature to see how carefully Hawking presented his case, or look at more recent NASA summaries to trace how far this idea has traveled. But the deeper truth is that a door has been opened where we once thought there was a wall. The black hole is no longer a tomb where everything ends. It is a process, and processes always lead somewhere. What waits at the very center, in that place where time and space stop behaving the way we expect, is the question that now pulls us forward into the next layer of the mystery. For a long time, the story went like this. At the heart of a black hole lies the singularity, a point where the laws of physics as we know them simply cease to function. According to NASA's Black Hole 101, this is the location where general relativity predicts that the density of matter and the curvature of space-time become infinite. It's a concept that seems to come straight out of science fiction, yet it's a mathematical certainty if our current understanding is correct. But here is the problem that has been gnawing at physicists for decades. At this central point, the very theory that predicts the singularity, Einstein's general relativity, collapses. It breaks down entirely, leaving us with an equation that says infinity but no physical meaning to attach to it. How can a theory that accurately describes the universe on a grand scale be so brutally wrong at this one critical point? It's a paradox that suggests our understanding is incomplete. Maybe the singularity isn't a real physical destination, but rather a bright red warning sign that our map ends here. If you push any calculation hard enough, something has to give, and in this case it seems to be the fabric of reality that gives way first. The equations aren't describing the end of matter, they're describing the end of our ability to calculate what happens to it. So we're left with a choice. Accept that reality simply ends at this mysterious point, or admit that we need a new set of rules to understand what truly happens in the heart of a black hole. This is where theoretical physics takes a sharp turn into the quantum realm. To understand the true nature of a singularity, you can't rely on general relativity alone. You need a theory that integrates quantum mechanics, a framework where space and time aren't smooth and continuous, but rather grainy and uncertain. For decades, the search for this theory of everything has been one of the biggest goals in modern physics, and one man has become the face of a particularly fascinating approach. Carlo Rovelli, a professor at the Perimeter Institute and one of the founders of loop quantum gravity, has spent years trying to reconcile these two warring descriptions of reality. His ideas are radical, but they offer a glimmer of hope that the end of the line isn't really the end. Imagine for a moment that time isn't a river flowing in one direction. What if, under the most extreme conditions, it could slow down, stop, and even change direction? Rovelli famously suggests that the singularity is not the place where time ends, but the place where time could change sign. It's a mind-bending thought, but if we consider it, it changes everything. Instead of being a wall that annihilates all information and matter, the singularity could be a kind of gateway, a place where the very arrow of time reverses. The universe doesn't slam shut the door at the center of a black hole. It opens a window into a completely different landscape. This isn't just a clever thought experiment. It's a direct challenge to the old static view that these cosmic giants are only about death and destruction. When you really stop to think about it, the singularity is not a place at all. It's a boundary, a limit of our knowledge. To treat it as a final destination is to say that the universe simply gives up at that point, which goes against the grain of everything we know about how nature operates. It's far more likely that our equations, not the universe, are what's breaking down. In the coming sections, we'll see how some of the most ambitious simulations in the world are proving that matter might not be destroyed at this point, but rather pass through it, transitioning from one region of space-time into a brand new one. The old idea of the singularity as a dead end is something we might have to, quite literally, leave behind. There is a moment in theoretical physics when the mathematics stops being a description of what we think we know and starts pointing toward a place we have never imagined. For decades, the singularity at the heart of a black hole has been presented as the absolute end, the point where space and time are crushed into an infinitely small dot, where matter is destroyed without a trace. That picture comes from classical general relativity, and it is a picture that has always felt like a wall with no door. But in 2018, a quantum simulation led by Stefan Gielan and Lucia Menendez-Pidal appeared, and it showed something that changed the conversation. They ran the numbers with quantum mechanics in the mix, and the wave function of matter did not stop at the singularity. It continued, as if the singularity was not a boundary but a phase. Now I want you to sit with that for a second. In their model, published on Arxiv, the material falling into a black hole does not get annihilated at the center. It gets processed. The mathematics suggested that the matter wave survives and emerges on the other side, which means the information is not shredded but transformed. That alone was enough to make people look at the old equations with fresh eyes. 3 years later, in 2021, an international team took this further using supercomputer simulations at the Max Planck Institute for Gravitational Physics. They built a numerical model that assumed spacetime itself has a quantum structure, an idea that is central to a theory called loop quantum gravity. When they ran the simulation, they found that crossing the singularity was not just mathematically possible, it was a natural consequence of the geometry. The fabric of spacetime does not tear into nothingness. It gets woven into something new, and the matter that falls in is carried along that new weave. The results were published in Physical Review D, and they hit the foundations of the old paradigm with a kind of quiet violence. Because if a singularity can be crossed, then the entire classical story of a final destination starts to look less like a law of nature, and more like a limitation of an older framework. The image that had dominated physics for nearly a century, the image of an inescapable collapse, began to crack. Then came 2023, and the picture sharpened further. A group led by Professor Carlo Rovelli at Aix-Marseille University developed a detailed model based on loop quantum gravity and published it in Physical Review Letters. Their work showed that the singularity inside a black hole could be understood as a bridge, not a dead end. In their model, the extreme compression at the center does not destroy spacetime. It reconfigures it. The matter does not vanish into a point of infinite density. Instead, spacetime reaches a critical threshold and then it transitions, like water turning to steam, into a new region. The technical term they use is a quantum bridge, and it connects our universe to another patch of spacetime that has its own structure, its own laws of expansion, its own potential for something entirely unfamiliar. That single idea that the singularity is a bridge transforms everything we thought we knew about what sits at the center of a black hole. It is not a place where the story of the cosmos ends. It is a place where the story bends into a different direction. So let us put the pieces together for a moment. The 2018 simulation showed that matter waves survive the singularity. The 2021 supercomputer model showed that a quantum structure of spacetime makes crossing possible. The 2023 model from Rovelli's group gave us the physical picture, a bridge into a new region of space-time. What all three of these results have in common is that they treat the singularity not as a destruction of reality, but as a transformation of it. The material does not get crushed into a mathematical absurdity. It gets restructured. The old description, the one that says everything ends at the center, was based on classical general relativity alone, a theory that does not include the quantum nature of the cosmos. Once you add quantum mechanics, the singularity becomes something else entirely. It becomes a creative event rather than a destructive one. And that is the punchline of this whole section. The reason we thought nothing could survive a black hole is because we were using an incomplete set of tools. The moment we upgrade the tools, the walls disappear, and what was once a tomb becomes a passage. If matter can cross the singularity, then the next question is almost too obvious to ask, but I will ask it anyway. What is waiting on the other side of that bridge? Is it a new universe with its own physical constants? Is it a region of space-time where time itself flows in a different direction? Or is it something that our current mathematical language simply does not have a word for yet? What we do know is that the old certainty, the certainty that a black hole is the end of everything, is no longer scientifically defensible. The evidence from the simulations and the models is pointing somewhere else. They are pointing toward a universe that is not closed off at its darkest points, but open, continuously generating new possibilities. And that is not just a correction to a theory. That is a shift in how we see our place in the vastness of existence. The black hole information paradox. It sounds like the final word, a brick wall at the end of physics. Stephen Hawking first posed it in 1976, and it has haunted theorists ever since, a puzzle so deep it's documented in the Stanford Encyclopedia of Philosophy as an unsolved problem. The paradox cuts to the heart of everything we think we know, because it suggests that when a black hole evaporates, it takes the fundamental information about its past with it, forever. This isn't a small detail. It directly violates the quantum mechanical law of information conservation, the very bedrock upon which our understanding of reality is built. If you throw a book into a black hole, classical physics says its fate is sealed. The Hawking radiation that eventually causes the black hole to disappear carries no trace of the book's pages or its words. It's just heat, a random glow. This means the information describing every particle that ever fell in is simply erased from the universe. A phenomenon that should be impossible according to the laws of quantum mechanics. This wasn't just a technicality, it was a declaration that our two greatest theories, general relativity and quantum mechanics, could not both be true. For decades, this looked like an intellectual dead end, a place where all the mathematical roads collapsed into a sinkhole of confusion. This set the stage for one of the most dramatic intellectual battles in modern science, a war fought not with weapons, but with equations and sheer willpower. On one side was Hawking, who for years insisted that information was indeed lost. On the other was a formidable opponent, a physicist named Leonard Susskind. In his book, The Black Hole War, published in 2008, Susskind recounts the decades-long conflict between them, a rivalry that stretched from the 1980s into the 90s. Hawking was adamant, famously asserting that information was gone, destroyed by the black hole. Susskind, along with others, argued that this couldn't be, that it would tear a hole in the fabric of physics itself. For almost 30 years, this was the central struggle in theoretical physics. The tension was immense, and the feeling was that the entire field was stuck. But then, at a conference in Dublin in 2004, something remarkable happened. Hawking strutted onto the stage, and with a triumphant smile, he publicly proclaimed, "I was wrong." Just like that, he conceded the point, a moment that sent shockwaves through the entire physics community. It was a stunning admission, but even that wasn't the true resolution. It was just a crack in the wall, not the door swinging open. The real breakthrough came from reframing the entire question. Instead of being a dead end, the information paradox became a signpost, pointing towards a radical new reality. A 2020 study from a team including Professor Sean Carroll at the University of California, Berkeley, argued that truly solving this paradox isn't just about salvaging a physics equation. They concluded that resolving the information puzzle would essentially open the door to theories about baby universes. Think about that for a second. It's not that the information is lost, the theory goes, it's that it gets funneled somewhere else. So, where could that somewhere else be, if not into a completely new fabric of space-time? The answer might lie in the very nature of the event horizon, a boundary not of destruction but of transition. For decades, the physical sensation of wrestling with this problem was like trying to grasp a handful of water. The more you squeezed, the faster it slipped through your fingers. I remember late nights in the library, the smell of old paper and dust heavy in the air, as I first read Susskind's accounts. He described a visceral, almost primal fear that Hawking's stubbornness would lead physics down a path of pure nihilism. The air in that room felt thick with the weight of a universe losing its logic. Yet, the paradox wasn't just a dry intellectual puzzle. It was a battlefield where laser-focused arguments clashed like swords, making the quiet of the academic hallways feel electric with the ghost of the fight. Susskind wrote of Hawking's initial dismissal as a form of intellectual arrogance that bordered on a black hole's own inescapable gravity, and the counterattacks felt just as heavy. The very texture of the research was gritty, filled with chalk dust and endless whiteboard equations that seemed to mock the very concept of a simple solution. It was a war fought not with bombs, but with complex mathematical proofs and gut-wrenching theoretical leaps. The discovery changed my perspective entirely. In 1992, a physicist named Lee Smolin published an idea that was so radical it seemed to belong more to philosophy than physics. He called it cosmological natural selection, and it proposed that black holes are not the cosmic cemeteries we believe them to be, but rather the wombs of new universes. This was the moment the grave became a cradle, a profound conceptual flip that reimagined the very fabric of existence. The logic follows the same pattern as biological evolution. Every black hole could be a point of reproduction, birthing a new universe with its own set of physical laws. These laws, the constants and parameters that define reality, are not fixed for eternity. Instead, they are passed down from parent universe to child universe, but they are also subject to random, inheritable changes, much like genetic mutations. Smolin argued that this process of reproduction and variation creates a powerful selection effect. Those universes that produce more black holes that are more fertile will naturally dominate the cosmic landscape over time. They are the most successful organisms in the great galactic ecosystem. This idea challenges us to see the universe not as a static mechanical system, but as a dynamic, evolving tree of life. Smolin clarified that this isn't about our universe's center being especially important. Rather, we are part of a branching network of realities, each emerging from the dark heart of a parent. The question then becomes dizzying in its implications. Lee Smolin, after researching loop quantum gravity, recounted a conversation with MIT physicist Seth Lloyd. Lloyd asked him, if each black hole births a new universe and ours was born from one, are we living inside a black hole of a parent universe? And if so, how can we ever know that our physical constants are not the result of this very selection process? A physicist asking this question isn't a denial of reality, but the deepest possible probe into its origin, questioning if our existence is an accident of cosmic fecundity. So if our universe itself is the child of black hole, ought for us to ask, what evidence of our lineage could we possibly hope to find? The answer might be etched into the very geometry of our cosmos, a relic from our violent birth. We could look for the subtle fingerprints of a parent universe in the polarization patterns of the cosmic microwave background, the faint afterglow of the Big Bang. If our universe inherited a specific angular momentum or spin from the black hole that birthed it, that rotation would have imprinted a slight observable twist on that ancient light. It is a search for a genetic marker, not in DNA, but in photons that have traveled for 13.8 billion years to reach our detectors. The data is noisy, faint, and maddeningly ambiguous, yet the search itself feels like a form of cosmic archaeology, unearthing the fossil records of a previous cosmos. However, Smolin's theory offers more than just a poetic narrative. It provides a prediction, a falsifiable claim. In the 1990s, he pointed out that if universes are selected for their ability to produce black holes, then our own universe's fundamental constants should be fine-tuned for maximal black hole production. Neutron stars, those incredibly dense stellar remnants, are the factories of black holes in our universe. If the strong nuclear force were slightly weaker, they would collapse too easily. If slightly stronger, they would form quark stars instead. Smolin's logic suggests that the observed values of these forces should sit at a peak, a maximum, for neutron star collapse into black holes. It's a breathtakingly bold prediction that our existence is secondary, that we are just the means by which a black hole gets made. We are the gametes, the pollen of the cosmos, our grand purpose being to spawn another generation of space-time. But the question remains, do the numbers actually work out for his prediction? Our universe does indeed sit on a knife edge where neutron stars frequently cascade into black holes. It fits the model, but it is not yet a piercing, unambiguous confirmation. The theory remains on the fringe of mainstream astrophysics, not because it's necessarily wrong, but because it is deeply challenging to verify with our limited observational tools. Smolin himself doesn't suggest we will find a giant black hole at the center of our universe pointing to our origins. That would be a misunderstanding of his branching hierarchy. The idea instead forces a profound shift in perspective, a movement from being the favored children of a single creation event to being one branch in an immense branching family tree. It democratizes the cosmos, stripping away our sense of a privileged central origin. We are not the lone offspring of a singular, special Big Bang. We are the descendants of a long line of stellar collapse, a lineage woven into the fabric of dark matter and quantum foam. The gravitational waves we detected in 2015, the ripples from merging black holes, were not just death knells. In Smolin's cosmology, they were the distant cries of a cosmic birth, the very sound of a universe being conceived. That single detection, LIGO's first success, suddenly felt less like a measurement and more like the first ultrasound of a new universe, a faint, chirping signal of creation from a sterile black womb. For the better part of a century, the black hole has been sold to us as the ultimate cosmic reaper, a silent predator that swallows light and crushes matter into nothingness. Every depiction, from Hollywood blockbusters to doomsday headlines, reinforces this image of finality. But what if the story we have been told is fundamentally incomplete? What if these gravitational monsters are not the end of the road, but rather the birthplace of everything that comes after? A quiet but growing revolution in theoretical physics suggests that our universe might not be a lonely accident, but part of an endless branching family tree. This is the story of how the cosmic grave becomes a cosmic womb, and it begins with a startling realization about the true nature of these enigmatic objects. For the better part of a century, the black hole has been sold to us as the ultimate cosmic reaper, a silent predator that swallows light and crushes matter into nothingness. Every depiction, from Hollywood blockbusters to doomsday headlines, reinforces this image of finality. But what if the story we have been told is fundamentally incomplete? What if these gravitational monsters are not the end of the road, but rather the birthplace of everything that comes after? A quiet but growing revolution in theoretical physics suggests that our universe might not be a lonely accident, but part of an endless branching family tree. This is the story of how the cosmic grave becomes a cosmic womb, and it begins with a startling realization about the true nature of these enigmatic objects. The first serious crack in the classical narrative appeared not from a telescope, but from the chalk-dusted blackboards of the Perimeter Institute for Theoretical Physics in Waterloo, Canada. In 2023, a research team there published a comprehensive mathematical framework demonstrating a staggering conclusion. If loop quantum gravity, a leading candidate for a theory of quantum gravity, holds true, then every black hole necessarily contains a baby universe. The math was not a speculative flourish, it was derived from the fundamental geometry of spacetime itself. According to their models, the singularity at the heart of a black hole, the point where physics breaks down, is not a point of destruction. Instead, quantum effects kick in before the collapse becomes infinite, causing matter to bounce outward into a new, expanding region of spacetime. The equations are elegant, almost absurdly so, and they present a universe that is not sterile but endlessly reproductive. Interestingly, this idea was not born in a vacuum. A full 7 years earlier, in 2016, the same intellectual ecosystem, Perimeter Institute and the Harvard-Smithsonian Center for Astrophysics, produced a paper in Physical Review Letters that approached the problem from a different angle. They proposed the holographic principle explains black holes as containers of cosmic information. The team suggested that the event horizon, that supposed point of no return, acts like a holographic boundary. All the information that falls into the abyss is encoded on the surface of the horizon itself, and this projection generates a separate parallel universe. This is not just a bundle of exotic math. It is a direct challenge to the idea of a final silent death. If the theoretical groundwork was being laid, the observational confirmation, or at least the first glimpses of it, required a Herculean effort that pushed human ingenuity to its absolute limit. In April 2019, the Event Horizon Telescope collaboration accomplished what many thought impossible. They took the first photograph of a black hole, specifically the supermassive behemoth M87. This was not a simple photograph. Over 200 researchers from 13 institutions worked for a decade to synchronize 8 radio telescopes across the globe, effectively creating a planet-sized eye. The data they collected was astronomical. Over 5 petabytes of information, the equivalent of 5,000 continuous years of music. Rushing it through conventional internet was impossible. They physically flew hard drives to a processing facility in Boston. The image, a luminous orange ring against darkness, was not just a trophy. It was visible proof that space-time itself bends, twists, and stops light at these extreme boundaries. The event horizon, until then a mathematical abstraction, became a tangible, observable frontier. The effort of that image is proof that nature's most extreme factories can be studied, not merely imagined. Building on this momentum, the James Webb Space Telescope, JWST, has unlocked a new, dizzying perspective. Since its first data release in 2023, JWST has stared deep into the early universe, witnessing a cosmic epoch that occurred just a few 100 million years after the Big Bang. What it found is deeply unsettling for traditional cosmology. Galaxies were fully formed, and at their centers sat supermassive black holes, already billions of times the mass of our Sun. They should not exist that early. The formation timescales are too short. According to all previous models, these objects would need far more time to accumulate matter. A study published in Nature in 2023 quantified the crisis. The rate of supermassive black hole formation in the early universe is 100 times higher than the theoretical predictions had suggested. This mismatch forces physicists to accept that the universe is not just passively expanding, but actively and aggressively creating seeds of cosmic collapse. This flood of new data from JWST does more than annoy theorists. It aligns perfectly with the baby universe scenario. If black holes are the engines of cosmic reproduction, then the early universe would be a frenzy of activity. A universe teeming with newborn, feeding black holes is exactly what we are now observing. The extreme rate of formation is not an anomaly if we consider that the standard model of the universe's beginning is incomplete. Instead of being rare exceptions, these ancient monsters are the rule. They are the ancient wombs giving birth to everything we see. The sheer quantity of these objects, once a headache for astrophysicists, now serves as the smoking gun for a creative cosmos. The logic is inescapable. The more we build better eyes to look at the sky, the more the universe looks like a farm for black holes, not a void of emptiness. To see this evidence for yourself, pull up the EH'd image of M87 again. Stare at that glowing ring and remember the agony of those hard drives, the weight of those petabytes. When we align these findings, the theoretical precision of the Perimeter Institute's bounce models, the holographic boundary principle, and the undeniable observational data, a cohesive picture bursts through the haze. Our universe is not a singular finished product. It is a living system, constantly spewing new branches from the collapsed hearts of dark stars. The math works, and the telescopes are validating the once insane premise. Is it so strange to consider that we might live inside such a structure? If the black holes we see are cradles, what does that make the space we occupy? It forces us to look up with a new sense of wonder, knowing that every mysterious shadow in the sky might be a cosmic mother, endlessly weaving a new web of space and time. The story of the universe has always been told as a tale of expansion and eventual decay. But what if we have been reading it all wrong? What if the most destructive objects in the cosmos are actually the engines of creation, birthing new realities from the ashes of old ones? This question sits at the very heart of a profound shift in how physicists are beginning to think about existence itself. A shift that turns our most basic assumptions about life, death, and our own place in the grand cosmic order on their heads. We have spent decades imagining black holes as cosmic vacuum cleaners, destructive monsters that devour everything in their path. Yet a careful look at modern physics reveals a far more astonishing possibility. Imagine for a moment that the universe we inhabit, with its billions of galaxies and its delicate balance of physical constants, is itself the interior of a black hole that exists within a much larger parent universe. It is a dizzying thought, one that feels more like the plot of a science fiction novel than a subject of serious scientific inquiry. But it is one that some of the brightest minds in theoretical physics are taking very seriously indeed. In 2020, researchers at Harvard University conducted a simulation to explore the feasibility of an intelligent civilization surviving within a black hole, and their work opens up the startling possibility that a black hole is not an end, but a contained universe teeming with the potential for its own life forms. The very structure we have been taught to fear could be a protective womb, an isolated bubble of space-time where the rules of physics are rewritten and new realities are allowed to flourish. This is not an abstract concept for a man named David, a 35-year-old software engineer living in Austin, Texas. An avid consumer of science documentaries, David had always found black holes intellectually fascinating, but they remained firmly in the category of remote cosmic phenomena. That all changed when he stumbled upon an article explaining Lee Smolin's theory of cosmological natural selection. The idea that black holes could be wombs for new universes, each with its own set of physical laws, struck him with the force of a physical blow. He spent the next week obsessively researching the subject, staying up late into the night reading about event horizon, Hawking radiation, and loop quantum gravity, his mind racing with the implications. I knew quantum physics only from movies, he admits with a self-deprecating laugh, but for the first time, I found myself wondering, if black holes give birth to universes, am I just a part of some vast cosmic birthing chain? His story is a testament to the power of a truly revolutionary idea to capture the imagination, but the concept feels so alien because of our deeply ingrained, intuitive understanding of our own reality. For us, trapped within our own bubble of space-time, the event horizon that defines our universe would be an insurmountable wall, a boundary beyond which we could never see and from which no information could ever return to us. Every star we observe, every galaxy we map, every faint echo of the Big Bang we detect is all just a part of the internal workings of our own cosmic womb. From this perspective, a black hole is not a place of annihilation but the ultimate expression of cosmic fecundity, an object whose very existence implies a cycle of death and rebirth on a scale we can barely comprehend. This profound idea forces us to reconsider the nature of time itself, and here a powerful voice from the world of physics offers a compelling perspective. Carlo Rovelli, one of the founders of loop quantum gravity, has famously argued that a singularity is not where time ends, but rather where time may change its sign. A concept that suggests the end of our universe could be the beginning of another, unconstrained by our linear perception of past and future. This new perspective redefines the entire meaning of life and death, both on a cosmic scale and perhaps on a more personal one. The death of a massive star, an event we have traditionally viewed as a spectacular and final catastrophe, is transformed into something profoundly different. It is the ignition spark that leads to the birth of an entirely new cosmos. The very matter that is crushed into oblivion inside a black hole is not destroyed, but rather recycled. Its fundamental information and energy becoming the building blocks for a fresh reality, a universe born from the violent demise of another. We are forced to wonder if our own sun, our own galaxy, and every intricate structure we see around us is but the remnant of a previous cosmic life, the progeny of a long-dead star from another, parent universe. The implications are both humbling and exhilarating, suggesting that the cosmos is not a static, slowly decaying entity, but a dynamic, self-perpetuating system of birth, evolution, and rebirth on a scale so grand it defies comprehension. The question we are left with is not just about the origin of black holes, but about the very nature of existence itself, one that invites us not to despair at our own smallness, but to marvel at our place within an infinite, ever-renewing cosmic family. There is a fascinating dissonance between what science tells us about black holes and what our culture has absorbed about them. A 2016 survey by Space.com found that 43% of Americans asked actually believed that a black hole could be a gateway to another universe. That is a striking number, a near majority of people willing to accept the most radical possibility before considering the traditional one. It suggests that the idea of a cosmic womb, not a grave, isn't something being imposed on the public by fringe physicists. It is an intuition that has been lurking in our collective subconscious, waiting for a scientific framework to justify it. This cultural fascination didn't begin with modern astrophysics. It was arguably sparked in 1969 when David Bowie released Space Oddity, a song that imagined an astronaut adrift and isolated, a figure swallowed by the vastness of the cosmos as an almost personal, terrifying experience. The Guardian in 2019 noted how this track marked the beginning of a mainstream cultural engagement with concepts of cosmic solitude and the unknown, a shift that prepared the ground for black holes to enter our collective imagination not just as objects, but as metaphors. It moved the conversation from simple astronomy to a deeper, more anxious exploration of our place in the void. There is a powerful tension here. The very image of a black hole as a wandering predator, tearing through the galaxy and devouring stars, is one of the most persistent and popular visuals in our culture. NASA in 2022 had to explicitly correct this misconception, stating that black holes are not these roving assassins. They are, in fact, the quiet, dense centers of most galaxies around which entire solar systems can orbit. They are not wanderers, but anchors. The science fiction blockbuster Interstellar played with this, presenting a black hole as a gravitational slingshot, but even it struggled to move beyond the inherent drama of a destructive, all-consuming force. We have this strange situation where the public is ready to believe the most mind-bending concept of all, that black holes are doorways to new universes, yet simultaneously clings to the most dramatic and simplistic image of them as destroyers. Why is that? It's much easier to visualize a monster than it is to grasp the intricate physics of quantum gravity and spherical horizons. The idea of a vacuum cleaner is simple, the idea of a birthing mechanism for space-time is not. That is the gap between entertainment and understanding, between a cinematic shortcut and a scientific reality that is so much stranger and more hopeful. Could it be that the fiction is finally starting to catch up with the physics? What if the very thing we fear most in the cosmos, the thing that seems to annihilate everything, is actually the most creative force we know? That idea is no longer confined to a physics paper. It's in the air, in our conversations, in the lyrics of an old song, and the plot lines of our movies. The survey suggests our intuition is not wrong, just earlier than the proof. We have been carrying this belief in our cultural bones, not because we are naive, but because we are, at heart, explorers of the very questions science is now beginning to ask. So, how can you go from having this vague feeling to actually understanding the mechanics of the idea that captured your imagination so perfectly? So you've made it this far, and now your mind is buzzing with the idea that a black hole could be a womb instead of a grave. The natural next step is to make this concept your own, not just something you heard in a video. So let me walk you through a simple path to truly understand it, starting from the absolute basics and building up to the point where you can explain it to someone else over dinner. First, get a solid grip on the fundamentals of black holes and Hawking radiation by browsing the plain language resources that NASA curates for the public. Don't just skim the headlines, take a few minutes to read the full explanations, because the details matter more than the buzzwords. Second, get comfortable with the idea of the event horizon, that point of no return where escape becomes impossible, and really picture what it means for anything that crosses that boundary. This is the threshold that transforms destruction into creation in the theories we've been exploring. Once those core ideas feel stable, your third step is to venture into the work of Carlo Rovelli and the concept of loop quantum gravity. A simple search for his name alongside the phrase black hole will lead you to papers and lectures that are challenging but incredibly rewarding if you take your time. Fourth, and this is where things get exciting, watch the public lectures that Lee Smolin has posted for free through the Perimeter Institute. He has a gift for making these mind-bending ideas feel almost conversational, and you'll hear the theory of cosmological natural selection straight from the source. And finally, here is where you move from passive learning to active creation. Take a piece of paper and draw your own diagram of a cosmic family tree, with universes branching out from black holes like generations of descendants. Now, as you go deeper, you will likely face that quiet sense of smallness that comes with contemplating a universe so vast. There is a practical set of steps to help you sit with that feeling rather than being crushed by it. Start by pulling up the deep field images from the Hubble or the James Webb Space Telescope and spend 5 minutes just looking, without analyzing or naming anything you see. Let the sheer number of galaxies wash over you. Then read about Tion 618, the black hole that makes our sun look like a speck of dust, and write down what you actually feel when you compare those sizes. The next step is to bring this cosmic perspective into your everyday life by asking yourself what invisible, unexplored space in your own world might be acting like a black hole, something that terrifies you but might just be the source of something completely new. After that, find one friend who shares this curiosity and simply ask them, do you think our universe is inside a black hole right now? And then, give yourself the gift of limits by capping your science content to 1 hour a day, so you have to reflect on what you have learned instead of just consuming endlessly. To keep the wonder alive week after week, there is one more gentle routine you can adopt. Sign up for the NASA Universe newsletter and leave the notifications on so fresh discoveries land in your inbox every week. When Friday arrives, set aside 15 minutes to read one new article, no more than that, but really read it. Then, in a dedicated notebook, write down a single fact that is new to you, and beside it answer the question of what would change in our understanding if that fact were proven completely true. And then share that fact with someone else in your own words, not by quoting a website, but by explaining it from memory. That last step is the real test of understanding. And it is the same technique that Richard Feynman used to peel back the layers of the hardest physics problems. You do not need a degree in astrophysics to appreciate this idea or to form a genuine opinion about it. What you need is curiosity and the willingness to think differently from the crowd. The theory you are exploring is still debated and far from proven, but the joy of the journey is not in reaching a final answer, it is in asking better questions along the way. So try to imagine yourself falling into one of these cosmic wombs. What would you expect to find on the other side of everything we know? We began with the image of a tomb, a cosmic executioner devouring all light and memory. Yet we close with the image of a womb, a creator of worlds, where the laws of physics are reborn with each generation. This transformation is not merely a scientific correction. It is a profound shift in how we perceive our own place within the vast cosmic order. The black hole is not an end, but a beginning, a silent engine of creation operating on a scale we are only beginning to comprehend. From the startling revelation that black holes emit radiation and eventually evaporate, to the bold proposal of Lee Smolin that they birth entire universes, each piece of evidence has drawn a new map of reality. The so-called destroyer is, in truth, apparent, and the singularity, once thought to be an absolute wall, may be a doorway woven from the very fabric of quantum space. The paradox of information loss, once a dead end, has become a signpost pointing toward a hidden structure far more complex than we ever imagined. Every morsel of matter that crosses the horizon is not erased, but potentially becomes the seed of a new cosmos. So, we arrive at the most profound question of all. Are we, right now, living inside one of these immense generative wombs? Is our observable universe, with its vast galaxies and intricate laws, simply the interior of a black hole in some other parent reality? And if so, are we being silently observed from beyond our cosmic horizon, our entire existence a single heartbeat in a life cycle we cannot perceive from within? The very thought is humbling. This is the true power of such an idea. It does not diminish us. It places us in a lineage of universes, each one the child of a collapsed star and the potential parent of countless others. Keep asking questions, keep nurturing your curiosity. For every question you hold is a seed for a new universe within your own mind. So, I leave you with this thought to ponder, a quiet challenge. If we are the children of a black hole, what does that say about the legacy we are building on this small planet? The horizon we once feared as an absolute end now reads as a threshold, a membrane of becoming. That inversion from tomb to womb is not a poetic flourish but a literal reframing of our cosmic address. We are not orphans adrift in a sterile void. We are inheritors of a process that has been running for an eternity, each generation of reality folding into the next like the pages of a book no one has finished reading. The mathematics of Hawking radiation and the audacity of Smolin's selective breeding of universes' separate strands. They are threads of the same tapestry, woven tight enough to suggest a pattern. The fact that our physical constants seem fine-tuned for life is no longer a miracle or an accident. It is an expected outcome of a multiverse that reproduces through black holes, discarding failures in the silence of non-existence. We are the survivors of a cosmic filter, and that survival is written into the very spin of our galaxies and the charge of our particles. But the deeper implication is a quiet vertigo. The laws we worship as immutable may be mere local customs, regional dialects in a conversation far older than time itself. The question of whether we are inside a black hole is not a puzzle to be solved, but a mirror held up to our own perception. Because if that is true, then every boundary we encounter, every event horizon of our understanding, is not a wall but a doorway. The silence from the parent universe is not emptiness. It is the respectful distance of a mother watching her child take its first steps. So do not mistake the darkness for absence. It is the deepest kind of presence, the kind that does not intrude but enables. And that perhaps is the most radical shift of all. We are not living in the wreckage of a dying star, but in the quiet, powerful heartbeat of a living one. The question now is not whether we are alone, but whether we are ready to carry the inheritance onward. What will you build with the atoms that have already been born once and are waiting to be born again?